Alright, so what we'll do today is we'll just review Laplace transforms.
You know those sheets, like that you can get, I want to say in like differential equation with all the formulas already there. Is that something that maybe we can use if we still have? Do you know the kind of sheet I'm talking about? Like it'll list the way the function works. Yeah, something like that. Yeah. If that makes sense. Did you see the ones he had?
So Laplace transform, by definition, Laplace transform is defined as. So I want you guys to pay attention and try to make it a habit not to take any notes. Just listen, go back and review the lecture. That way you'll be better off. That is just a suggestion. If you want to take notes, that's fine.
What page are you on?
Page 35. This is how you define the Laplace transform. Okay. So here, what you're seeing here is we use the symbol L, this L, to represent Laplace. Okay. So the way you read this is some function of time. If you take the Laplace of this function time, which is represented by capital F of x. It's defined as integration of 0 to infinity. You put this function here. You add an e to the power of minus st dt and you take the integration. Now for the purpose of course, you don't have to do this. Maybe for the first exam, I might ask you one function, I might give you one function and ask you to derive the Laplace transform. But for most of the course, for majority of the course, you don't have to worry about it. Now, what is the use of a Laplace transform? Recall differential equations. Okay? Now, if you look at differential equations, if you have a real world problem, okay, you apply physics and you define that problem in terms of mathematics, right? All physics can be expressed in mathematics. It has to be expressed in mathematics. It should be able to express it in mathematics. Right? And then what you do is, so this would be a differential equation.
The mathematical
The
expression.
mathematics you develop would generally be a differential equation. It could be anything. It could be algebra, it could be geometry, but in our case it will be a differential equation. And all of you are comfortable with differential equations. Okay? So what you do is, typically what you do, if you have a differential equation, you seek a mathematics solution, right? All these differential equations have solutions, correct? And then you go back to you interpret the solution, you interpret the mathematics, and that will lead to the real world solution. Okay, this is the process most. So this is a solution to differential equation. Okay, now you have to understand differential equations are functions of time, correct? At least we are going to deal with differential equations which are functions of time. You understand? What do you mean by functions of time? Right? So if you look at f equal to ma, in most cases, f is a function of time. What does that mean? The function changes, the force f can change with time. M may also change with time. Acceleration is again a function of time, right? So that is, how do you get to that? That's a differential equation, correct? That's what order of differential equation is it?
Acceleration.
It's a second order differential equation. F equal to ma is a second order differential equation, right? Where do you get that? That's based on physics. That's based on laws of physics, right? Because Newton's second law. Now you look at a real world problem and apply that law to that real world problem. F is equal to ma is a general representation of the law, but that law, how you represent that law for a particular problem keeps changing. That is the differential equation. Okay. So once you have a differential equation, what you have done, you have defined the problem statement in terms of mathematics. Okay. Now you seek a mathematical solution. All differential equations, not all, but most differential equations have mathematical solution. Irrespective of what it means, there is always that is what you have been taught in differential equations. Have you studied ordinary differential equations? To some extent? Ordinary, ODEs and PDEs. Have you studied differential equations?
Yeah.
So differential equations, if you study differential equations, you would have probably studied the ordinary differential equations. Okay? So you just look at those ordinary differential equations. And what do? You use some existing solution to find a solution to that ODE, right? Or that differential equation. That solution means something, right? You seek a mathematical solution, but that means something. Now that is what you interpret and say that is the real world solution, right? Now what you are going to do, if you look at f equal to ma, what solution are you going to seek? So if you have f is equal to d over dt of mb, right? You are going to seek a solution. What is this v? V is d over dt of x, position, you are seeking a solution for x when you do your actual solution to this differential equation. So what does this x mean? That's the position. So now you understand, right? So if you are trying to fly your plane, you'll apply this and you'll formulate how the velocity of or how the momentum of the plane is changing with respect to the applied force or the thrust. And then when you solve for this at any given instance of time, you're going to get this x, which is the position of that plane, right? Or an aircraft. That is what you need. Okay. Now, where does this Laplace transform come into picture?
When you have a differential. I just know you take the Laplace transforms and you
Why Laplace transforms? The question is why Laplace transforms. Okay. See, every function, just like any function can be expressed as a function of time, it can be expressed as a function of frequency as well. What is frequency? What is the relationship between time and frequency? Hmm? 1 over time is frequency. Okay? So S here is a frequency variable. Okay? And T is a time variable. Okay? Now what we do is we will still follow this process, but we'll add an additional step. Here, let's do so real world problem, physics, differential equation. Laplace transform, inverse Laplace transform, okay. So what we do is we take this differential equation. If you take the Laplace transform of a differential equation, that function, the f of t is a function, it's a differential equation. If you take the Laplace, what you get is a Laplace transform. Okay, f of s is the f of s is the Laplace transform of f of t. Okay, where s is the Laplace variable or the frequency variable and t is the time variable. So this is also, you can say this is frequency, or it's also called Laplace variable. Okay.
So the reason that we're doing, the reason it's Laplace transform is because anytime you have f of t, it will become, we will have to use Laplace transform with that.
You don't have to. If you take the Laplace transform, you are going to get a f of s. It converts a function of time into function of frequency. You understand function of time? Everybody understands function of time? Right? There are quantities which are function of time, there are quantities which are not function of time. Right? Any system is a function of time. The dynamics of any system is a function of time. Statics, not so much. Okay, statics don't change. That's the reason.
I guess my question is, when you say why Laplace transform, it didn't have to be Laplace transform. We could have technically did it another way.
Right. So you could have just, that's what, you look at this one and this one. We are taking this is an extra step. And there is a reason for taking this extra step. Okay? We could have just gone from here to here. And that's what you have been doing until now. You have been taught how to take the differential equation of form a differential equation based on physics, and then seek a solution, and then figure out what that solution means, or understand what that solution means. But now we are going to take this step. There is a whole new set of solutions available in this domain. That is the reason we use this. Whatever solution sets are available in this domain, so you have what you have. You have multiplied, you have added a new set of solutions by just converting that to frequency variable. And we understand systems can be understood differently. The dynamics of system can be understood differently when you convert that to frequency domain. Okay? So what do you understand by frequency domain? For example, your conversations are at a much lower frequency. The noise is at a much higher frequency. Your aircraft movements are at very low frequencies. Right? You don't do this. They are very low frequency. But the noise coming into the aircraft, the vibrations, the oscillations are at very high frequency. So we can pass through, we can neglect those noise parameters when we treat them as functions of frequency. And that's what control is about. Control is a lot about frequency, understanding what is an input, what is a noise. Okay? So we are going to seek a different set of solutions here. And although the table she just showed is a comprehensive table, most of this thing would be limited to taking Laplace transform of differential equations. So by the time, let's say by second test or even before midterm, you will not use any other Laplace transform other than using it for differential equations. Got it? So for example, if you have d square, let's say a function f of t is equal to d square x plus d x, let's say 2 plus dx of t is equal to think about this Q of Q is the applied force, and this is your this is what you get applying Newton's laws, right? Now, when you take the Laplace of this, you are going to just end up with Q of S is equal to S square x of S plus 2 S x of S plus 3. So if you see, these two are, this is a differential equation, this is a Laplace transform. There is a very nice, very easy pattern if you look at it. Q of t becomes, any Q of t becomes Q of S. See here, x of t becomes x of S. If it's a double derivative, what does it become? So you have an S square added to it, Okay, because s square is a frequency variable, and then you have x of s. If it's a single derivative, right, dx of dt, it becomes 2s. There is s added, x of s.
Okay. Now, for the first one, that's not an x, is it? No, the one on top, the little cube. What is that variable?
X.
Okay.
So what we do is, for differential equations, we don't use capitals. We use small letters, and even this is small letters. So if you notice, everything here is small letters. Everything here is capital letters, except the variables. The s square and t are not capital. Yes, John.
Didn't you say that time is 1 over frequency?
Mm-hmm.
So why isn't it 1 over s squared?
It's not always that straightforward. Frequencies can be expressed as 1 over time. So here, this is a Laplace variable. Okay. So this is, if it's a function, it's not a direct correlation of a function. So here, if you see, this is a function, right? You cannot just take, how are you going to take 1 over s? You cannot just say x of t doesn't mean anything. It's not a, what does this mathematically mean anything?
No.
It's just a representation, it's a notation. So this is not, you cannot do that. Because again, this is a notation for a function. This means something. Got it? Okay, this mathematically means something. This mathematically doesn't mean anything. It's just a notation for a function of time. So this, if you do this, it doesn't make sense. So if you want to convert any function of time to function of frequency, you use this. This is one form of converting that. Okay? So the mathematics of this is beyond the scope of this course. Okay, you don't want to take it to that. Not here. Maybe later. Okay? So this is Laplace transform. Now we'll also look at the definition of inverse Laplace transform. Inverse Laplace transform is represented by this. We have f of x equal to
like why Laplace transform?
Huh? I just told you, this has a whole new set of solutions.
So how it is useful for our course library? Why?
When you're trying to control something, right? You have to first understand what you want to control. When you say what you want to control, you have to understand the dynamics of the system. It cannot be just random control, right? It has to be based on some science. So what is the science? When you do this, so what are you trying to control here? You may be trying to control the position. Okay, you may be trying to control the speed, for example, or the velocity. How do you try to control the velocity? By regulating this force. So you have to understand what you want to control, and then how you want to control. And if you want to understand that, you have to understand the dynamics. You understand? Making sense?
But still there is no Laplace. But still there is no Laplace transform.
Yeah, dynamics are expressed. This will be here, this differential equation. Laplace transform is again the dynamics expressed as a function of frequency. Laplace transform is again dynamics expressed as a function of frequency. And you seek a solution to the dynamics. No? You still don't understand? Why do you take differential equations? Tell me. Why do you formulate differential equations?
I say like to understand the dynamics.
Why do you want to understand the dynamics?
To see how the system is changing, how it works.
Right. So exactly. So what is the only difference between differential equation and Laplace transform is When you express differential equations, it's a function of time. When you do express it, when you take Laplace, it's a function of frequency.
Yes, so this shows. This is relative.
This domain, mathematics, is different domains. You have algebra, you have geometry, you have calculus. This is calculus.
See, I think so. After differentiation, we just like do these to understand what kind of solution we might get.
What kind of?
Solution we get like with these terms. That's what I mean.
So this phase is the problem.
Right.
So when you take the Laplace, it is still expressing the problem as a function of frequency. Now you seek a solution to that frequency problem as a function of frequency. And if you take the inverse Laplace transform of that solution, you get a time-based solution. In control, you have to understand both frequency and time. You have to have a sense of both frequency and time. So that is the reason we go into Laplace transform. If you do, you can always, there is also a set of solutions or control based on just time-based solutions. We'll look at that as well. But we'll review this and we'll go back to time. Okay. Now, the inverse Laplace transform definition, again, you don't have to use this. Okay. Okay. So here, when I say S, again, S is a frequency variable. Okay. And it's generally expressed as a complex number or complex variable. Okay. So this is inverse Laplace transform and this is Laplace transform. What you need to focus on this and focus on this and try to understand why we need Laplace transform. Okay. Try to go back and review why you formulate differential equation. This is the engineering you need to do. For anything you do, you have to understand what is engineering. Engineering is this. You seek out a real world problem. You apply physics. Okay? You express that physics in mathematics. That becomes your problem statement. And then you seek a mathematical solution and then interpret that as real world solution. This is the process of engineering. Any engineering. This is the core of engineering. So what is engineering? By definition, what do you understand by engineering? You understand engineering? No?
Yes. We almost graduated up.
The engineering is applied physics, applied mathematics, right? So do you see that here?
Is it safe to say that we take these complex variables and these real world problems? Is it safe to say that we take these real world problems that are complex and we use Laplace transforms to make them simple algebraic problems to solve?
No, the Laplace, this S frequency has to be expressed, needs to be expressed as a complex variable. Because you have to capture the magnitude and the phase. So we'll discuss that.
Is that J the imaginary?
J is the imaginary. So this is the real part. This is we use J in the textbook because I'm also used to I, but the textbook, I don't want to confuse you guys with what the textbook uses and then using an I.
So just say just check.
Alright, so this, let's say for example, you have f of t equal to a e to the power of minus at u of t. Okay? So if I ask you to, this is an example, find f of s. Right? So you are going to just use the formula I gave you, or you're going to look at the table. The solution, you can say table 2.1. Okay, so here f of s is equal to L. It is simply this. Now we can actually, I can derive this. Let me do it once. So we have integration of a into integration of 0 to infinity. E to the power of minus at. This is the function itself. Now we have to add e to the power of minus st, right? Just look at your this thing. dt, you keep u of t.
You said just look at what?
Look at the definition of what this Laplace transform. So this, the definition I gave you on the board. If you look at that, the function, this function f of t into e to the power of minus st will be there. Okay. This is a. A is just a constant. That will come out. E to the power of minus at, e to the power of minus st can be written as e to the power of minus s plus a t u of t dt. Now you have to understand u of t is nothing but a unit step function. Okay. Here u of t is a unit step function. And it's defined by u of t is equal to 1 for t greater than 0 and it's equal to 0 for t less than 0. Okay. So since you are integrating between 0 and infinity, it's almost like saying this is just 1. You understand? It's beyond s. There is nothing before s, before 0. Right? You understand?
I don't.
U of t. You understand this definition? u of t is equal to 1 for t greater than 0. So if you plot this, so here is your t and here is your u of t. Okay. Now let's say your t starts at 0. It is simply this is 1. Okay. So this is the value of u of t. After time t equal to 0, it is simply 1. It keeps on being 1. If it was here, what would the function of t be? What would the value of t be on this part of the time scale? It will be 0. After time, we don't really understand negative time, right? We understand only positive time. So as long as time is positive, u of t is simply 1. Okay? So here we are integrating in positive time between 0 and infinity. So this, we'll finish this and let's go on. So what is the integration of e to the power of minus s plus t, s plus at? Do you remember? It will be a into 1 it will still be e to the power of minus s plus a, right? Divided by s plus a.
You can still put that T up.
Huh?
That T still needs to go.
This t will be here. Correct? And this has to be evaluated between 0 and infinity. And this will be negative. Okay? Agree?
That's right.
However,
Huh?
you said that for the purposes of this class, the table will do.
Right.
Okay. So
So I'll just derive this once. Okay. So you have, if you evaluate it at infinity. So what is e to the power of infinity minus infinity?
see the 0 will do.
It cannot be either, it's math.
It's 1 to 0.
It's so you have the e to the power of minus t. E to the power of minus infinity is equal to e to the power of 1 over e to the power of infinity. You get it?
Say that one more time.
E to the power of minus something minus x is 1 over e to the power of x. Okay? So if you have this, if you evaluate this at infinity, it is 0. Because what happens is, it is e to the power of minus infinity. Okay, t is equal to infinity. That is 1 over e to the power of infinity. Anything raised to the infinity is infinity. Okay? So 1 over infinity is 0. So it will be 0 minus, or what will it be? Minus a over s plus a into, so you have to only evaluate this numerator. It is e to the power of 0 is what? Anything raised to 0 is 1. So this will be a over s plus a. F of s is equal to. Okay? So this function is, this is the function of, this is the Laplace equivalent. Now you really don't have to remember all of this. You have to just know how to look at the table and figure this out. So similarly, there will be an inverse Laplace transform. So we need not discuss, or just give me a couple of minutes, we'll just finish off. So if you have, similarly, Just give me a couple of minutes, okay? Just 2 minutes. We'll just finish. F of s is equal to 1 over s plus 3 square. Just look at this one and this one. So here everything will be in terms of s. Okay. Some of you will somehow get a t here. Don't do that. The variable t should not appear in your Laplace transform. So now it will be find inverse Laplace transform. So what we do is we generally do this, right? I love that. So you apply that formula. Okay. Now, for the sake of this course, you don't have to really apply the formula. If you look up the inverse Laplace transform table, I'll give you the Laplace table. Again, it's the same table. You have to reverse it. Okay. So here, f of t is equal to L inverse f of s, which is equal to e to the power of minus 3t t u. Okay. Just pay a little bit of attention, it's actually very simple. So you see s plus 3, s plus a, right? You see a. Here what is the numerator? It's just 1, so there is only 1. Now you see this 3 of t, e to the power of minus a of t. This square is captured in this t. That's the only difference. You see it?
I don't see
If it
that.
was cubed, what would this be? T square. It would be e to the power of minus 3t, t square, u of t. If it was cubed. Got it?
Yeah.
So you have to compare this one. Everything is the same, except that there is an additional t here. Okay? So this is, if it is cubed, what would this be?
I'm asking you.
It will be t square.
Okay.
If it is s plus t to the power of 4, what will this t be? T. That's it. Okay? Please give me your attendance.